Hello everyone, my name is Elsayed. I'm a research scientist at the Google Brain team in Mountain View, California. So today I want to talk about our work on revisiting spatial invariance with low-rank local connectivity. This work is joint work with Prajit Ramachandran, Jonathan Schlins, and Simon Kolbeth. So the main question we're trying to address in this work is whether spatial invariance in convolution is a good inductive bias. So as you may know, convolutional architecture perform better than locally connected on computer vision problems. So both convolution and locally connected layers assume local receptive fields as an inductive bias. However, the main distinction is that convolution requires spatial invariance in the learned parameters. So what I mean here by spatial invariance is that local filter banks is shared and applied equally across space. In contrast, locally connected layers would have different filter banks that's applied in each location in the space. So it may seem intuitive why convolution works well in computer vision. For example, it doesn't make sense to apply different kernels at places in an image that have the similar appearance. However, what we're proposing here is that it may also seem overly restrictive to apply the same kernel at locations that have different properties. And that's what we're trying to address in this work. So the main hypothesis we're trying to address here is spatial invariance is overly restrictive. So if spatial invariance is truly a good inductive bias, and if we have a tool that allows us to relax spatial invariance in convolution and make us traverse the space from convolution to locally connected layers, we'd expect that accuracy would drop as we deviate from convolution and go towards locally connected performance. However, if spatial invariance is overly restrictive, we'd expect that there's going to be an optimal point in between, where some degree of relaxation of spatial invariance is actually better than either convolution or locally connected alone. So the main contribution of this work is actually to design this tool that allows us to relax spatial invariance and make us traverse the space from convolution towards locally connected layers in a controlled manner. And that's what we term as low-rank locally connected layer. So to understand this layer, let's go back to convolution. So in convolution, you'd have one filter bank that's applied in each location in the space equally. And by doing this, we achieve spatial invariance. Whereas in locally connected layers, you would have n-filter banks, and each location would receive a different filter bank. And this layer is spatially varying. So a low-rank locally connected layer would be somewhere in between. So it would have a k filter banks, and then for each location in the space, we're going to linearly combine these filter banks to construct a filter that's going to be applied for that location in the space. So this is what we term as the rank of the layer, which is the number of kernel bases that we combine. So this terminology reflects that this layer kernel would have some low rank factorization in the spatial dimension. So the low rank layer here, by controlling the rank of the layer, we can traverse the space from convolution. So if rank is equal to 1, the layer converges to a convolution, and if rank is equal to n, the layer converges to a locally connected layer. So to understand this further, take, for example, this 3x3 low-rank locally connected layer with rank 2. So rank 2 reflects that you have two kernels, each of which is of size 3x3 by channels in and by channels out. And then for each location in the space, we can linearly combine these filters to construct a filter that's going to be applied to that location. So the combining weights and the filter banks are going to be learned here end-to-end. And the combining weight could be either fixed or can vary based on each input example. So now to validate our hypothesis that convolution is an overly restrictive inductive bias, we conduct an experiment on MNIST FAR10 and CelebA on a 3-layer network. So these are our results. So on the x-axis here, we have the rank of the low-rank locally connected layer. So as rank increases, the degree of spatial invariance decreases. So we relax spatial invariance as we increase rank. And we deviate more from convolution architecture. So what you see here, as you relax spatial invariance, the accuracy of this layer increases, as stipulated by our hypothesis that spatial invariance is overly restrictive inductive bias. So also, if you compare this layer to locally connected, coordinate conv, or even a convolution layer that have more channels, we can see that the performance of our layer is actually much higher, which shows that convolution is actually over restrictive, and actually this layer could be used in computer vision. So just to summarize, so we design here a low-rank locally connected layer, and we use this layer to test whether spatial invariance and overly restrictive inductive bias. And our results here suggest that as you relax spatial invariance, in classification problems, accuracy increases. So please check our paper, and also we have open sourced the code. Thank you very much.